Alrighty, welcome back. We're just going to do a couple of examples of graphing some trig functions, just to help you see kind of what's going on with the different parts of the trig functions and how they actually display on a graph. If you hear also some random meowing, it's because my cat is in the room with me. So yes. Anyway, what is graphing? Well, we kind of know what graphing is, right? So I'm not going to explain the basics of what graphing is, but just particularly in relation to our trig functions, we know that our trig functions all derive from the unit circle, right? We have this unit circle, and then we have this line that we rotate, and this point measures cos x or cos theta, sine theta, and then tan theta is made up of those things and that sort of thing, right? But we notice because it's a circle, the trig functions are called circular. You've probably seen that in your books already. Okay. They're called circular, and this means they repeat. And because they repeat, what that's going to mean is that, so we can say this means the graphs of the functions will also repeat, right? Because as we take intervals of 2 pi around the unit circle, cos and sine and tangent will all repeat each other. So it will also repeat. And this makes them look like waves. What we call waves. Okay? Things that look roughly like this. That's a really bad wave, actually. Let me do it again. Something that looks like this, right? Or something that looks like this. Okay? And these are the different things that we make with our graphs, okay? So I'm going to assume that you know what the basic sine, cosine, and tan graphs look like. If not, just go look in your book. We're going to be working with some more complex ones, okay? Or parts where we adjust things. So without further ado, let's dive into it. Example 1. Y equals cos of 2 theta, and we're going to graph this from theta ranging in between 0 and 2 pi. Okay, so the first things first is we just have to remember what the basic cos graph looks like. So basic cosine graph is something like this, where it does this, and it kind of keeps coming up. This is 1, and these are pi on 2, and then sort of this symmetry line is pi, and so on. Okay, this is 3 pi on 2, and so on and so forth. Okay, sort of waves. So what we do is we can recognize this a couple of different ways. I'm going to do them both just to give you an idea of what's going on. So we'll do the algebraic approach, and then we'll have a look at what I like to call the transformational approach. So the algebra of it is we need to figure out where are the x-intercepts. Okay, where are the x-intercepts? Originally, for cosine, they're at pi on 2 and 3 pi on 2. But that's not going to fly for this one because we're not graphing cos of theta. We're graphing cos of 2 theta. So when we have y-intercepts, what do we always do? X-intercepts, we set y to equal 0. So we say 0 is equal to cos of 2 theta. Okay? And now we solve this equation. So we want to solve it for theta. So we go, what is the inverse cos of 0? Okay, equals 2 pi. Cool. So we think, what's the inverse cos of 0? Well, what angles give us a cosine or x value of 0? Well, that's going to be pi on 2, 3 pi on 2, okay, equals 2 theta. Now, we want the values ranging between 0 to 2 pi. So currently, this is the only values, but we are going to divide by 2, right, which is going to halve all of our values. So some people like to do this now, where you can look at my solving equations episode if you want to go back and check. Some people like to get the extra solutions now because they know that they're going to need to divide, or some people like to divide and then grab the extra solutions later. I'm of the second opinion. I like to just grab my normal solutions here and then grab the rest later. So I'm going to do that. So we're going to go to here. We divide by 2, which means we get pi on 4 and 3 pi on 4. okay? But this doesn't range all the way up to 2 pi. So what I'm going to do is I'm going to notice what interval is happening in between here. Well, this interval is an interval of pi on 2, right? So I'm going to keep adding intervals of pi on 2 until I get up to 2 pi. So we get 5 pi on 4. Cool. And we get 7 pi on 4. And these are all equal to theta, okay, for when y equals 0. In other words, these are going to be our x-intercepts, okay? So we check that and we go, great. And now we can graph our, well, we can graph right now, but I'm going to do one more step. We're going to say, where's the y-intercept? Okay. And we can set here x equals 0. Well, not x equals 0, but I guess theta equals 0. Okay, so y is equal to cos of 0, which is equal to 1. In other words, it hasn't moved anywhere horizontally or vertically. It stays at 1. Things just get compacted a little bit. Okay, so we can graph it now. We can graph. So we say the graph is like this. Okay, and we're going to go from 1 down to -1. Okay. It's going to kind of do this. It's going to be a little bit more squished. Obviously, this is a sketch. So this is pi on 4, 3 pi on 4, 5 pi on 4, 7 pi on 4. And then this peak here is going to be at 2 pi. Okay? In other words, it's been squished in half. Okay? So that's how you would graph it algebraically, but you can also do it via transformation. So I'm going to do this in, what color should I do? Maybe I'll do it in this color. Let's do it in green. So by transformation, you should check with your teacher what they would prefer. I'm happy with either one, but by transformation, we can see that there's nothing in front, or there's no number here. So we can say no change in amplitude. Amplitude, if you don't remember, is this distance. It's how high or low the graph will go from its peaks and troughs, at least if you're starting at 0. If you're not starting at 0, you just shift everything down. Okay. We also notice that there's nothing here. There's no vertical translation. And there's also nothing getting added here. Okay. It's actually like a +0. So we can say or horizontal. Some teachers like the word shift, so that's also fine. The only thing that has really changed, the only change is the period, okay, which comes from here. This is the period shift. Okay, because it's 2, it means everything is getting doubled, which means that our period is actually going to be, our period is 2 pi divided by 2, which is equal to pi, which tells us that our graph is going to repeat itself every pi intervals instead of every 2 pi intervals, which makes sense because this line here is exactly pi. Okay, so you could kind of use those transformations to figure out what the graph is actually going to look like. And that might be a bit more helpful later when the algebra gets a bit tricky. All right, example number 2, y equals tan of 3 theta. Now your books will say that there's no sort of left and right shifts that can happen with tangent, which is fair enough because it gets a little bit iffy. You could do it and it could be fine, but it prefers to mainly do period shifts, okay? So again, I'm going to do the algebra and then we're going to do the transformation. So maybe I'll give myself a bit more space. Let's do the algebra first. So we know that tangent kind of roughly looks like this when we start anyway. This is tan theta. It kind of looks like this. And there's got asymptotes here. Ugh, this shouldn't be dotted. This should be. Just like this. Where are these asymptotes? Well, they're at pi on 2. It's where tangent is undefined. Okay, so it's pi. This is 3 pi on 2. We'll do one more just to be clear of what's going on. I keep drawing a dotted line. And that's 2 pi. Okay. Whoa, sorry, not 2 pi. That's not 2 pi. It's 5 pi on 2. Great. This is 2 pi. Okay. So something is not right. What is not right? Whoa, I've done this very, very badly. My apologies. Just kind of ignore everything that I just said for there. So again, even your teachers make mistakes when they're kind of doing it on the fly. I've just defined my intervals kind of badly. Tangent actually has a period of pi because it repeats itself every pi interval. So this should be pi. Okay. And this should be 3 pi on 2. And this should be 2 pi. That's better. Okay, my bad. All right, so now we can ask, where are the x ints? I always have trouble with tangent. Okay, so, it should be y. Again, we set, what do? We set y to equal 0. Nothing changes. Set y equals 0. So we get 0 is equal to tan of 3 theta. Okay, and then we go tan inverse of 0 is equal to 3 theta. Okay, and now we think what angles within 0 and 2 pi from here give us a tan value of 0. Okay, and those angles are exactly, well, 0 is going to be one of them. So 0, pi, 2 pi. Okay, we can kind of ignore 0 because it's just going to get divided off anyway. Equals 3 theta. Now again, I'm the sort of person who likes to divide first and then grab the extra angles. Some other teachers, which is fine, might say, well, you know you're going to divide by 3, so you can just multiply this thing by 3 to get your thing, but it doesn't really matter too much. So again, we get pi on 3, then we get 2 pi on 3. Okay. In other words, our interval or our period is changing from pi to pi on 3. Okay. And then I can just keep adding until I get to 2 pi. I know it's working in intervals of pi on 3, so I can get pi, 4 pi on 3, 5 pi on 3, 2 pi. Okay. They're all going to be equal to theta. Great. And then we can ask ourselves, where is the y-int? Again, let's set x, or theta equals 0. So y is equal to tan of 3 times 0. Tan of 0 is just 0, so y equals 0. So nothing has changed, okay? So again, we graph. Let's make it a bit longer because it is going to be actually quite long. I'll make sure I label it properly this time. Okay, so we know that our asymptotes are going to move, okay? But we also know where our x-ints should be. So how about we do that first? Let's go like this, okay? That's 0. Let's draw this line and we'll figure out where this line is in a sec, but let's just keep going. So like this, we know this first one is over here. So that should be pi on 3. I might run out of room here, but you'll get the idea. 2 pi on 3. Pi. 4 pi on 3. I might be able to fit it. I might just have to squish it in. Obviously not to scale. 5 pi on 3. Let's just spin a bit. And we'll stop there. 2 pi. Okay. And then these asymptotes, you can try to solve for these asymptotes algebraically, but you kind of don't need to, because really what we've done is we've just compacted it, and this is where the transformation method is really helpful. We can see our transformations. The main one is that the period has shifted. Period shift to, tan has a period of pi, right? So it's pi divided by 3, which equals pi on 3. Okay, so it's a pi on 3 period, which means it's going to repeat itself every pi on 3, which basically means everything has gotten divided by 3. So we can say everything divides by 3, which means you can know where these asymptotes are, because the original ones were here at pi on 2 and 3 pi on 2. So the new ones are going to be at this thing divided by 2. So pi on 2 divided by 3 was pi on 6. Okay, and then you get 3 pi on 6, which is pi on 2, and then so on and so forth, right? And you can keep going, which is awesome. All right. That's good. Yeah, that's how we would graph this tangent function. All right, let's do the last one. The last one's a bit more involved. Alrighty, this is example 3. Apologies if my mic sounds a little bit different. It just died, so I'm just having to use the inbuilt mic from the iPad, which I think is a little bit louder. So, okay, but we're at example 3. This one we're going to do slightly differently, mainly because there's a bit more going on. So we're going to look at the transformations first, get a general idea of what the graph looks like, and then find the x-intercepts, okay? So let's have a look. We know that sine kind of looks like this. Boom, 1, -1, and so on, okay? So let's have a look at the transformations. So the transformations, let's do them one at a time, from left to right. So there's an amplitude shift, or amplitude increase, to 2. There's a period shift. Sine usually has a period of 2 pi, so we'll divide it by 2. There's a horizontal shift. Now, which way is this going? Well, that's positive, so it's going to go the other way. So it's going to go left shift by pi on 4. Then the last one is a downward shift by 1. Okay, now this is going to be helpful because now we can sketch the graph and get an idea of what's actually happening, and it'll be important for our x-intercepts as well. So we know that the downward shift means that our axis of symmetry has shifted down to here. Okay, so it's shifted down to here, our axis of symmetry, at -1. I'm going to need to extend this actually. We know that there's an amplitude increase to 2, which means that the peak is going to reach at 2 and it's going to come down to -3. Okay. We know that the period shift means it's going to get compressed inwards, and the left shift by 4 means it's going to do something slightly like this. I don't know why I'm dotting the line. Okay. It's going to do something like this. Now, why is that important? It's important because of 2 things. One, the y-intercept has changed. Okay, so we're going to need to go find that. But I think more importantly, the x-intercepts have changed. And very importantly, they're no longer in a nice even interval. Okay, so our x-intercepts are going to have different distances, which means that it's going to be much easier to list them all out first in the given range from up here, and then work the equation from there, which we'll do now. Okay, so let's find the x-intercepts. This is going to get a bit algebra heavy, so feel free to pause if you need to catch up. Set y equals 0. Okay, 0 equals 2 sine 2 theta plus pi on 4 minus 1. So 1 over 2 equals 2 sine 2 theta plus pi on 4. Oh, sorry, we already divided by 2, so that goes away. So we can take the sine inverse of 1 over 2 and make that equal to 2 theta plus pi on 4. And now we can draw a exact value triangle, right? And we can say what values or what angles give us a sine value of positive a half. Again, we play on easy mode and usually we'll give you one which has one of these exact value triangles. So it's going to be this one, okay? And we're going to say it's going to be in quadrant 1 and 2 because this thing was positive. Okay? So we can write our equation out. We can write it as, I'm going to write them in 2 different colors so we can see what we mean by adding in the extra ones. Pi on 6 and 5 pi on 6 are 2 solutions. Now, technically, if we were working in 0 to 2 pi, this gives us all we need. But because we have a period shift, okay, because our period has been shifted and it's going to get divided by 2, we're going to take this number and we're going to times it by 2. That's going to be equal to 4 pi. And so we're going to add the solutions that get us to 4 pi, knowing that they're going to be divided by 2 to get back within the range. We're sort of overextending, knowing that the division is going to bring them back in. So what are the angles up to 4 pi? Well, we get 13 pi on 6, and then we get 17 pi on 6, okay, is all equal to 2 theta plus pi on 4, okay? And now we just take away pi on 4 from all of them. Just solving, nothing too crazy. Okay, now we could actually pull a nice trick here. Well, not a nice trick. We can show or maybe recognize that this thing is going to be negative, right? But our range told us specifically that it could only be greater than 0, which means we can just get rid of that. We don't need it, which is cool. So then we just do the other ones. Bit of algebra. Feel free to fast forward if you trust the algebra here. I'm just going to do it quickly. Well, hopefully quickly anyway. 10 pi on 12 minus 3 pi on 12. 7 pi on 12. 13 pi on 6 minus pi on 4 equals 26 pi on 12 minus 3 pi on 12 equals 23 pi on 12. And last one, 17 pi on 6 minus pi on 4 equals 34 pi on 12 minus pi on 4. 3 pi on 12. Which equals 31 pi on 12. Okay, so these are our 3 solutions, and we get, where should I write it? Yeah, let's write it up here. We'll go up this way. We'll do our y-intercept underneath. So we get 7 pi on 12, 23 pi on 12, and 31 pi on 12 is all equal to 2 theta. Okay. Notice that those intervals are consistent, which makes sense, right? Here to here, not the same. Which makes sense because our graph got shifted. See the red? This bit? Okay, now we just divide by 2. 7 pi on 24, 23 pi on 24, and 31 pi on 24. And that's all we get. So those are our intercepts. So we can say 7 pi on 24, 23 pi on 24, and 31 pi on 24. Yay. And now, to be thorough, we should find our y-intercept.
set x or theta equals 0. Okay, so y is equal to 2 sine 2 times 0 plus pi on 4 minus 1, which is equal to 2 sine of pi on 4 minus 1, which is 1 over root 2. I'm just getting my exact values here. If you don't trust me, go back and have a look, which is 2 over root 2 minus 1. We'll just leave it as that. You can combine the fraction, but who cares? So that's the y-intercept. We could label that, if we really want to, 2 root 2 minus, but not 2 root 2. Well, technically it would be actually if we rationalize, but it doesn't really matter. Minus 1. Okay? And we're done. So that one's a little bit more involved, probably a bit of a blueberry cheesecake graphing question. But yeah, now you know how to graph. So you've got these 3 examples. Go back and have a look if you need to. Have fun.